Today we're looking at strong and weak acids and bases. We've kind of touched upon strong and weak acids back in the grade 10. When we wrapped up acids and bases, or at least those were in my class last year. So just a few things. Strong acids, an acid that dissociates completely into ions in water is called a strong acid. So the idea of dissociation is where the actual compound, the acid itself, breaks apart into its respective anions and cations. Right? So the idea of HCl breaking apart into H pluses and Cl negatives. Right? Now, according to that, so if we looked at the dissociation of hydrochloric acid in the form of so we have the HCl aqueous, and it dissociated into H plus aqueous plus Cl negative aqueous. Right? Whose theory does that follow? The A guy, yeah. Who's the A guy? Arrhenius, right? So we had the Arrhenius. Because what do we not take into consideration with this? Water, right? It's aqueous solution. So where is the water in this? But this is what we mean by dissociation. When you see the term dissociation, and excuse the messy writing, so we're breaking apart into the cations, right, positive charges, and the anions, which are the negative charges. So all molecules of hydrochloric acid in an aqueous solution dissociate into H plus ions and Cl negative ions. So the whole idea that every single time, every molecule, or every molecule of the HCl is actually going to break apart from itself. It's not going to remain. So that's what the dissociation. So we saw that breakdown. All of them are going to do that. Now, the H plus ions, as we know, as we've talked about, remember, it's just a proton. Remember, no neutrons in the hydrogen atom. Okay? So we lose the electron, and it's just a proton. So remember, we know that they don't exist, they don't really exist alone in solution. So they always kind of bind itself to a water molecule, forming this hydronium ion. The hydronium ion, the H3O plus, that is our, let's say, our so-called conjugate acid, as we talked about in the previous chapter. The concentration of hydronium ion in a dilute solution of a strong acid is equal to the concentration of the acid. So if we have 1 mole per liter, okay, or 1 molarity solution of hydrochloric acid, it will contain the same concentration of the actual acid itself, of the actual ion itself, the hydronium ion. Okay, so we have it here in this little table. So if we put in, let's say, we put in just as a number, just to explain, right? We're putting in 100 molecules, let's say, of HCl in water. All 100 molecules of HCl are going to break apart to forming our conjugate acids and conjugate bases. Right? So we're going to have 100 molecules of the HCl, and we're going to form 100 molecules, let's say, of the hydronium ion and its respective anion, okay, which will represent our conjugate base. So all of them will break apart. All of them will form those ions. And that's what we mean by strong acids. So strong acids, literally all of them will dissociate as such. Here I have an example on the side here of some typical strong acids. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, HI, nitric acid, sulfuric acid, and perchloric acid. So these are common strong acids, and yes, you do need to know these. So memorize these strong acids. Weak acids. A weak acid is an acid that dissociates very slightly in a water solution. Only a small percent of the acid molecules break apart into ions. So acetic acid, common acid found in vinegar, is considered a weak acid. Okay. as it says here, about 1% of the actual acetic acid will actually dissociate, meaning the remaining 99% remains intact as the acetic acid formula. And I'm going to show you that in just a second. And that 1% translates to 0.1 moles per liter of concentration that will actually dissociate into the respective ions. So, the number of acid molecules that dissociate depend on the concentration and temperature of the solution. So, of course, as temperature increases, so will the ability to dissociate. Concentration of hydronium ions in a solution of a weak acid is always less than the concentration of the dissolved acid. So here we have an example. So before dissociation, here is acetic acid, CH3COOH. When it dissociates, it gives off that proton, that hydrogen proton, to water. And I'll give it to water, forming the hydronium ion. And here, if we looked at it in terms of numbers, right? So hypothetically, if we had 100 molecules of acetic acid in water, only one of them will actually break apart. Only one of them will dissociate and give off the hydrogen to the water, forming the hydronium ion, which will leave only one of them, which will remain as its conjugate base. Which means the other 99 acetic acid molecules will remain in its full uninterrupted formula. Okay. So the molecule will appear as is. It will not give off. So 99 out of the 100 will not give off that hydrogen proton to the water to form the hydronium ion. So we're only going to form one hydronium ion. Right? Remember that concentration, as we're going to see, right? The concentration of this is what's going to determine pretty much the type of acid, what kind of a pH level that this acid is going to give. And we're going to get to concentration and pH levels towards the end of this chapter. So a few acids contain only a single hydrogen ion that can actually dissociate. So all the ones that we've looked at, hydrochloric acid, the acetic acid, they only give off one hydrogen. Right? So these acids are called monoprotic acids. So mono meaning one, protic refers to proton. So how many protons can it give, right? Remember, when that hydrogen is given off, right, it loses the electron, positively charged, that proton pretty much tacks on to water molecules, forming the hydronium ion. Right? So as we said, hydrochloric acid, hydrobromic acid, hydroiodic acid. Right? These were three of the examples of the strong acids that I showed you guys in the previous slides. But these are considered strong monoprotic acids. But don't worry about that. Just be able to identify, if I asked you to identify a monoprotic. But you can still name these as strong acids. Right? These are just strong acids. But we know that it's monoprotic because hydrochloric, well, it's H combining with a Cl. Right? So it's only one H with the Cl. One H with the iodine. One H with the bromine. So we can only give off one proton of hydrogen. Hydrofluoric acid, HF, also a monoprotic acid, but it's considered a weak monoprotic acid, or just, we can look at it as a weak acid. So it's similar to acetic acid. Acetic acid, even though it's got the CH3, it can only give off that one hydrogen. So it's also considered monoprotic. Many acids contain two or more hydrogen ions that can dissociate. So sulfuric acid, the H's we can actually give off. H2CO4, SO4, is the formula for sulfuric acid, which means it can actually give off two hydrogens. Right? When it gives off those two hydrogens, it's able to give off two protons. So when it dissociates, right? The first time, it gives off one hydrogen proton. Who's it going to give it off to? The water. Which leaves us with the HSO4 -1, because we've given off one proton. This sulfuric acid is considered a strong acid, right? As I've shown you guys in the list of strong acids on one of the earlier slides. Now, it dissociates once, but it has the ability to dissociate again. So we can still remove this hydrogen and give off another hydrogen to a water molecule, to another water molecule, forming that another hydronium ion. Right? The only thing is now this is considered the strong acid, but when we dissociate this one, okay, it's considered a weak acid. Okay, so the resulting aqueous hydrogen sulfate ion, HSO4, considered a weak ion. So when it dissociates, right? So here's now the weak version of the acid, but it's in ion form. It also can give off the hydrogen proton to a water molecule, forming the hydronium ion, right? And then giving way to the sulfate ion. Now, notice here one of the differences, what I've used. Arrows going back and forth. What it means is this reaction is actually reversible. So, as quickly as this is able to dissociate into this and this, right? These same two things will come together to reform the weak acid. So it's it goes back and forth. It's kind of like they come apart and then they come together. Go apart, come together. So this is reversible, right? And so you'll see arrows that go back and forth, or you'll see the arrow just going in one direction. Right? So this is, okay, when this dissociates, it's a strong acid, they will all dissociate this way. Right? Then this will dissociate again, but it's reversible. It goes back and forth because it is a weak acid. Acids that contain two hydrogen ions dissociate to form two anions. These acids are sometimes called diprotic acids. So we've got the monoprotic because it can give off one proton. Diprotic because it can give off two protons. So sulfuric acid, one of the examples. Carbonic acid, another example. Right? Anytime you see H2 with the formula for an acid, it can give off those two hydrogen protons. So the acid that is formed in the first dissociation is always stronger than the acid that is formed in the second dissociation. So even though an acid might be a weak acid that has the H2, that first dissociation is always going to be still stronger than the second dissociation. So that acid that it forms, the first acid is always stronger. Right? So once it dissociates once, that acid is still stronger than the new ion that it forms. Acids that contain three hydrogen ions are called triprotic acid. Common one is phosphoric acid, H3PO4 in aqueous. Right? So here we have H3PO4. We can give off three hydrogen protons, okay, when we dissociate it in water. So we have the following. H3PO4 is going to give off the hydrogen to the water to form the hydronium ion. But when it dissociates here as follows, we form this ion. This ion still has two more hydrogens that it can give off. So what's going to happen is in a water solution, right? And I just what I've done is I haven't shown the hydronium ion in these examples. I just wanted to show the dissociation of the hydrogen proton. So we've got the hydrogen proton being given off, right? And pretty much it's tacking onto water. But it has the ability to give off two more, right? So we have the following. So here we have the ion that we formed in this first one, this first dissociation. So now this second one is going to give off one more, right? So we've given off, which means I still have one more proton that I can actually still dissociate. I can still give that up. So what's going to happen is this is going to dissociate again. Okay. So we have a total of 3 hydrogen protons that we can actually give up. That will give up to a water molecule forming the hydronium ion. Right? But as we said, the first one is always considered stronger than the second acid. This second acid is still stronger, even though it's weaker, than this one. So this first reaction is more likely to happen, and then all the others make way. But again, notice how they're reversible. So the acid that is formed by the first dissociation, as I said, stronger than the acid that is formed by the second and then by the third. So the third would be the not as strong, the acid for the dissociation. First one's always the one more likely to happen, and then the others are always usually reversible. So strong bases and weak bases. I have here a few examples of some strong bases. Sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. Notice common polyatomic, right? Hydroxide. We have looked at a base that does not contain, right? Other bases that don't contain the hydroxide are certain oxides, right? So certain metals combined with oxide, not just hydroxide, form bases as well. And we'll look at that in a second. Recap that again. So a strong base dissociates completely into ions in water. So the same goes with strong bases as we did with strong acids. So if a strong acid dissociates completely in water, so will a strong base. Okay. So all oxides and hydroxides of alkaline metals, so anything in group 1 combined with oxide, right? So something like, so here's a group 1 alkaline metal, sodium, combines with oxide to form Na2O. These are what we call the oxides, right? Sodium oxide. These are also considered bases. Okay. So all oxides and hydroxides of alkaline metals, as well as all oxides and hydroxides of all alkaline earth metals from below beryllium. So if you look at where beryllium is, so magnesium oxide, calcium oxide, so all those just below beryllium will also form bases as well. So it's not just the hydroxide. So even that's the hint that we know we've got a base, right? But also be careful that you may have oxygen, like an oxide as such in your examples. Concentration of hydroxide ions in a dilute solution of a strong base is equal to the concentration of the base. So if we had 1 mole per liter solution of sodium hydroxide, which is our strong base, we will also have the same concentration of hydroxide ions as we start with, right? So which means all of them will dissociate into its respective ions. So barium hydroxide, strontium hydroxide, all strong bases, so they will all break apart, giving off the hydroxide ion. Okay, so they will all dissociate, just like we had with the strong acids. Magnesium oxide and magnesium hydroxides are also considered strong bases, but here they're actually considered insoluble in water, but they're still considered strong bases. Small amount of these compounds do dissolve. Remember we said, even though something is insoluble in water, there is still a very tiny percentage that actually does dissolve in water. And that tiny percentage is what actually can dissociate. And when it does, when those few little molecules that actually do dissolve in water, they will actually dissociate completely in water. So most bases are considered weak bases, except for that list I gave you guys. I gave you guys a list. Make sure you do memorize that list. A weak base dissociates very slightly in a water solution. So similar to weak acids, where 1% actually dissociates in water, which leaves the entire molecule intact. Right? So most common weak acid, ammonia. Right? And ammonia is one of those that doesn't really look like it's a base, right? It's NH3. So it doesn't have the hydroxide as we know, but we know that it does work because what happens is, who gives off the hydrogen proton? Is it ammonia or is it the water? The water, right? So the water is going to give off a proton, the hydrogen proton, to ammonia, which makes the water act like what? An acid, exactly. Right? So to kind of recap last class's lesson. So the water acts as the acid, the ammonia here acts as the base. So, which gives off pretty much our conjugate acid and our conjugate base, right? The OH. We still have the OH. Right? So, as a weak acid, only 1% will actually dissociate like this. 0.1 moles per liter will actually dissociate like this. The remaining molecules of ammonia will actually remain as such. So, power of the hydrogen. So here we're going to be looking at pH. I'm just reminding you guys about pH, but this time we're actually going to be making some calculations on pH. All aqueous solutions contain ions. Even pure water contains a few ions that are produced by the dissociation of water molecules. So water itself can actually, when they combine together, really tiny amount, right? Remember, we talked about last class, one property of acids and bases is that they conduct electricity, right? We can actually light up a little, light bulb. But we put that those same contacts into water, pure water, it will not light the light bulb, right? Which kind of proves that there's no conductivity in the water, but there is a really tiny percentage, but it's so tiny that it goes unrecognized in water. So the ions recombine to form actual water molecules. So what we have is, we have the two water molecules, and notice how it's reversible, and that's why. Really tiny percentage that actually undergo that, where one of them will give off a hydrogen to the other, right? Forming the hydronium ion and the hydroxide ion. So our conjugate acid, conjugate base. Does it really matter which one's the acid or base? No, we can't really identify which one. But one of them acts as an acid, the other one actually acts as a base. Okay, notice it's reversible because these two will react back to form the water molecules again. On average, at 25 degrees Celsius, only about 2 water molecules in a billion. Okay, so 2 molecules of water in a billion will actually dissociate as such. Okay, that's at those conditions. So ions in solution usually conduct electricity. That's why pretty much there are really no ions in water molecules, right? That's why it makes water is not considered a good conductor. Chemists have determined that the concentration of hydronium ions in neutral water at 25 degrees Celsius is only 1.0 times 10 to the power of 7 moles per liter. Right? So that is the typical concentration of the hydronium ion in pure water. So here we have the 2 water molecules, those 2 water molecules in a billion that will dissociate as such. So the dissociation of water also produces the exact same tiny amount of hydroxide ions. So we have equal amounts of this and equal amounts of this. So if we have an equal amount of acid and an equal amount of a base, right, we really don't have, right? Here's where we're now, just to kind of jump the gun a little bit, but it's a recap from last year. Remember, what is a neutral pH? What is the neutral number for pH? It's at 7. Right? Because we've got an equal number of hydronium ions as we do hydroxide ions. Right? So if we have this concentration of the hydronium ion, we also will have this same concentration of the hydroxide ion. So whatever, and one thing you're going to notice now with acids and bases, we're going to be using these square brackets. These square brackets, right? The way we read this is the concentration of hydronium ion is equal to the concentration of the hydroxide ion, which is equal to 1.0 times 10 to the power of 7 moles per liter. Okay? So we read square brackets as the concentration of whatever we have in these square brackets. That's how we read the square brackets. So please make sure you use square brackets accordingly with some of the problems that you'll have, sample problems you'll have at the end of the chapter. So here we have the hydronium ion equal to the concentration. So the concentration of the hydronium ion is equal to the concentration of the hydroxide ion. What kind of a solution do we have? We have the equal number of acids as we do bases. What kind of a solution do we have? Starts with the letter N. Neutral, right? So a neutral solution. Right? We have a neutral solution. They equal to one another. If the hydronium ion let's use the proper terminology when we use the square brackets. The concentration, the concentration of the hydronium ion is greater than the concentration of the hydroxide ion. What kind of a solution do we have? An acidic solution. Now, if the concentration of the hydronium ion is less than the concentration of the hydroxide ion, we have a basic solution. So please be able to read what that means, right? Concentration of whatever's in the square brackets. And notice here some of the mathematical terms: greater than, equal to, you should know, and less than. pH scale measuring by powers of 10. The concentration of hydronium ions ranges from about 10 moles per liter for a very concentrated strong acid to about 10 to the power of negative 15 moles per liter for a concentrated strong base. Okay, one opposite, to each opposite end of the spectrum on the pH scale. In 1909, a Danish biochemist called Sorensen suggested a method for converting concentrations to positive numbers. So, what we have here is pretty much what we're going to be looking at is a numerical system of logarithms. Have you guys in math done logs? Use the log key on your calculator? No, not yet? Okay, we're going to be doing it. I'm not going to go through explaining too much about really logs and logarithms. That's what your math teacher should be doing. Okay, and really all you need to know is how to put these numbers into the calculator. That's really what I'm going to show you guys. Real simple. These are really real simple calculations that we're going to be doing. So you're going to see it. Now, just to touch upon what your math teacher will be teaching you about logarithms. The logarithm of a number is the power of to which you must raise 10 to equal that number. So, the logarithm of 10 is, so 10 is my base in the logarithm. What is 10 going to be to the power of that will give me also 10? 1. So, the logarithm of 10 is 1. Because 10 to the power of 1 is equal to 10. So that's what we're, just to kind of, just a recap, just to kind of give you guys a little insight about what logarithms. The logarithm of 100 is, again, same thing. What is 10 going to be to the power of that will give me 100? 2. Right? Because 10 to the power of 2 is 100. Okay, so far pretty simple, right? I think nothing too fancy. Sorensen defined pH is equal to negative log of H positive, right? The hydrogen proton. But obviously, if we're using the hydrogen proton, right? Remember Arrhenius, as we talked about at the beginning, was the one responsible for that theory, that the hydrogen dissociated, right? But he never took into account the fact that there was water, right? So we're going to rewrite the formula. This is now the formula you need to know. That the pH, to calculate pH of something, is equal to the negative log of the concentration of the hydronium ion. So regardless of whether you're calculating an acid or a base, the pH scale, remember, power of the hydrogen, how many of these, what is the concentration of that in solution? Right? If something is basic, still there are going to be some, hydronium ions, but not as many as there would be in acids. Right? The stronger the acid, the higher the concentration of the hydronium ion. Right? So, what does pH really stand for? Well, we're looking at power, right? Power of 10. Right? That's why we're calculating the logarithms. Logarithms is 10 to the power of something. Right? So what power of 10 to the something is going to give me whatever number we're looking for, the logarithm of something. And then H stands for the concentration of the hydrogen ion, but not really the hydrogen ion, it's the concentration of the hydronium ion. So what we're looking for is the actual concentration of the hydronium ion in moles per liter. Okay? Or capital M, moles, or molarity. So capital M, moles per liter, or in moles per liter. Okay, so you're probably panicking, going, "Oh my goodness, this calculation, it's gonna freak me out." It really is. It's really simple. So we're gonna look at, as we said here, the concentrations of the hydronium ion and the hydroxide ion, right? And figuring out which one is greater than or equal to or less than will determine what kind of a pH. And here what we have is just a few examples of certain everyday things around us and their pH level. Again, something you don't really have to memorize, but have an idea of whether it's considered acidic or basic. So let's look at the first sample problem. Calculate the pH of a solution with the concentration of the hydronium ion being 3.8 times 10 to the power of -3. Right? So how do I write this in the formula? So what is the formula? The formula is pH is equal to negative log and the concentration of the hydronium ion. So what I'm going to do in here is I'm going to substitute 3.8 times 10 to the power of -3 into this H3O. Okay, into the hydronium. And that's what I'm going to get. So I'm going to put that into my calculator. The only thing I won't be able to put into my calculator is that moles per liter. So let me get out the calculator here. I've got the following. So when we're putting in the calculation, let me just, I have the numbers because I don't have the numbers right now on me. So if we're trying to calculate, we hit the negative button on our calculator, right? We're going to hit the log button, right? Negative log, and we're going to put in the numbers 3.8, but we're not going to hit times 10, right? We're actually going to hit the exponent button, and you can see it here. You're looking for either the little EE on your calculator or the EXP. So you're looking for a button that shows you as EE or the button that is EXP. This will bring up some kind of letter as such, or maybe your calculator. And what really this means what all this means here is the base of times 10. That's really what that little e stands for. And then we're going to put in the remainder, which is negative 3. Okay, because we've opened up the brackets, okay, or it opened up the brackets when we put it in. Maybe your calculator doesn't, but if it did, close the brackets, okay, and then hit equal. So there is our answer. 2.420216, and it goes on. Now, how many significant digits in my question? 2. So my answer should only include this 2.4, right? We're going to look at the number immediately following that. Will it change anything? No. So the answer is the pH is equal to 2.4. So what kind of a solution do we have? It's an acidic solution. We know from this, based on this pH level, we have our ammonium concentration, we have our hydroxide concentration. Is the concentration going to be equal, less than, or greater than? Greater than. So the concentration of the hydronium ion is going to be greater than the hydroxide ion. Last sample problem. Calculate the pH of a solution with H3O positive is equal to 8.27 times 10 to the power of negative 12 moles per liter. So, same thing. Let's get our calculator out. Let's clear the history here. And same thing, right? We are putting in negative log. It opens the brackets. We put in our concentration, 8.27, right? Again, as I said, you don't put the times 10, right? We're going to put the EE, right? And then our negative 12. Again, when you're putting in this information, make sure that you do not use the subtraction button. Okay? So do not use this button, right? Do not use your minus button to put your negatives in. Actually look for the negative button on your calculator when you're putting that in. So you're going to hit that, right? We're going to hit equal, and we get 11.0824949. How many significant digits in my question? 3. So we want the 11.0. We're going to look at the number immediately following that. And the pH is equal to 11.1. So what kind of a solution do we have? Basic solution. So we have a base. So the concentration of the hydronium ion, and with respect to the concentration of the hydroxide ion, is going to be equal, greater than, less than? Less than. So the hydronium ion is going to, concentration of the hydronium ion is less than the concentration of the hydroxide ion. We've already just looked at calculating the pH of the hydronium ion. So to do that, we just find the negative log of the actual concentration of the hydronium ion. Now, what happens if we're given the pH? So what we're going to be looking at right now to wrap up the lesson is to find the concentration of something, or sorry, to find the concentration of something when we're given the actual pH. So to do that, well, what's the reverse step of log? Well, we've already talked about log and how, or the logarithms, and how we were trying to find the logarithm of something, right? And it was always a base of 10. So 10 was the base to some kind of an exponent, and that exponent, in fact, is the pH. So the equation to find the concentration of the hydronium ion is equal to 10 to the power of a negative pH. So what we do is 10 is our base, right? Our logarithms, as we said. and our exponent is negative and whatever the pH value is. So let's look at it. It'll make a little more sense when we look at the first practice problem. So here's the first practice problem for these type of equations. Calculate the concentration of the hydronium ion for a solution with a pH of 4.5. So we start off with our main equation. So the concentration of the hydronium ion is equal to 10 to the power of a negative pH. So I put it in red because that's what we're going to substitute this 4.5 into. And it's going to look as follows. The concentration of the hydronium ion is equal to 10 to the exponent, or to the power of, negative 4.5. This 4.5 is the pH value from our question. So we throw that into the calculator, and we get the following answer. And this answer that we get in our calculator of 3.1623 times 10 to the power of negative 5 is our concentration of the ammonium ion in moles per liter. But now, we've got two significant digits in our question, which means we need two significant digits from our answer. So we want the 3.1. We're going to look at the number immediately following it, and the answer for this question becomes the concentration of the hydronium ion is equal to 3.2 times 10 to the power of negative 4 moles per liter. Let's look at one final sample problem dealing with the same type of question. So calculate the concentration of the hydronium ion for a solution with the pH of 10 to the power, or 10.25. So same thing. To find the concentration of the hydronium ion, it's equal to 10 to the power of negative pH. So what is the pH? 10 to the power of negative 10.25, right? This negative 10.25 from this pH value. Throw that into your calculator, and we get the following concentration for the hydronium ion in moles per liter. So the question has four significant digits, so we want the 5.623. We look at the number immediately following that, and it doesn't change anything. So the answer for this question becomes 5.623 times 10 to the power of negative 11 moles per liter.